looking at a ball that is being dropped. This little image over here is supposed to represent two things. We have the dial piece that is going to represent the speed of our object. So we start with a speed of 0. After 1 second of time, we accelerate so that we have a speed of 9.8 meters per second. They just kind of rounded this off to 10 to make the numbers a little bit cleaner for us. If we have an object that is falling for 2 seconds, it has accelerated for 2 seconds at a rate of negative 9.8 meters per second squared. So our speed would come out to 19.6, which again, for simplicity's sake, we're just going to round that off to the 20, because what we want you to see is that the speed is going to change in equal intervals, right? If we say that gravity is pretty close to 10, we can see that there's a pretty clear pattern. Now, what I would do in my physics class is I would just use this equation. So let's just jump down here to a time of 6 seconds. If they wanted to know how fast is my velocity moving, well, this is a ball that was dropped only one time. And the initial velocity here would have been 0 because it starts at the highest point. All dropped objects have an initial velocity of 0, whatever your logic there. So my initial velocity would be 0. My acceleration rate would be a negative 9.8, and my time would be 6 seconds. Now, for simplicity's sake, just so that you aren't getting caught up on the numbers, I am going to go ahead and I'm going to take this value of negative 9.8 and I'm going to round it to 10, just so we get pretty numbers and we're not messing with decimals right now. So if I do that, I simply just have gravity times time. So I get a negative 60 because we started with no velocity. If the question is asking for the velocity, negative 60 meters per second is my answer. But here we are really just looking at the speed. How I know that? Because this is a speedometer, because there are no negative numbers on my dial here. So they're really just asking for the magnitude of how fast is my object going. So I would say my object has a speed of 60 meters per second. And if you look at this picture, this very last picture that goes with the 6 seconds, that is indeed what the dial is at. I initially filled in the picture by just comprehending what it meant for it to change by an acceleration rate of 9.8 meters per second. But I wanted you to see that you could also use the equation to jump to that answer. Now, this paper is a very nice instructional tool to just introduce the concepts, but you will not work problems like this in your practice packet, on a quiz, on a test. Instead, you're going to be given information that lets you know the object was dropped, it's fallen for 6 seconds, what is the speed? And so you're just going to jump to the formula, okay? The other equation that I have here for you is showing us a process by which we would take this formula from our kinematics equation, and we're using this to show how far has the object fallen. So you can see here's how far the object went in the first second. This distance traveled in the second is larger. Why is that? Well, because he's going faster. So if the ball is going faster, then he went a greater distance in the 1 second. If he goes even faster, well, he's going to travel even more distance in 1 second. And so the spacing is going to be different between each 1 second snapshot. So if we want to know how far has the object fallen, well, now we're going to use this equation to determine that. Again, because my object is starting with an initial velocity of 0, which actually on the picture would be right here. If he's starting with an initial velocity of 0, then when I do my calculation, this number here just simplifies to 0. Oh, but it's supposed to be times time. Yes, but anything times 0 is 0. If I want to know how far has he fallen after 6 seconds, 6 times 0 is still just 0. So this first part of the equation just becomes 0. Then I'm going to add 1/2 of gravity times time, and remember that's the value that's being squared. So if I'm being asked what is the displacement of my falling object, here's how my numbers plug in. Even though we're way down here for our question, the information comes from the single dropped object. So once again, for simplicity's sake, we're going to take this value of 9.8 and we're just going to round it to 10 just so we don't have to worry about decimals for right now. So I'm going to end up with 1/2 of 10 times 6 squared. So -5 times 36. And so if I do -5 times 36, I have to actually do that one. Sorry, I don't know that off the top of my head. That's going to give me 180. So here, I actually calculate a -180 meters as my displacement. That's my calculation. Now, why did my displacement come out to be a negative number? Remember, displacement is directional. So the ball started up here where the boy is. At 6 seconds, it's down here below where the boy has started, or where the drop started. So because the object is physically located below the starting point, that gives it a negative value because down is negative and up is positive. Here in the illustration, they're asking us to fill in the distance using an odometer. Remember, that would be just the scalar version of how far. That's my distance. So I would just write 180 in that picture. But the way that I came to that value was by calculating where this D technically stands for displacement. And we're going to then determine whether or not we need to include the negative in this answer. So since it says what is the distance on the handout, we're just going to take the 180. If the question says what is the displacement, you must include the negative 180. Why does it matter? Because if we had a value of positive 180, that means that the ball is somewhere above the boy's head, but he dropped it. So it's somewhere below him, right? Do you understand the difference? Again, later when we start doing more things with our objects rather than just dropping them, those directional pieces are going to be so much more important in your just understanding of what is happening in addition to answering questions. So I want to make sure that I spent some time going over that with you as well. Okay, the last thing that I want to point out on this slide here is I took the equation and I wrote it a couple of different times. So in my class, you are going to continue to see D equals VIT plus 1/2 AT squared. That's the way that I'm going to write it for us all of the time. But we've been using this equation where this was a car driving down the road, right? So how am I supposed to know that I'm using -9.8 for my acceleration rate? Well, you have to understand that the object is accelerating because gravity is acting on the object. Now, these other two formats are just different ways that you might see the equation expressed. If you're looking at, I don't know, maybe you're looking at an online resource. Maybe you're sitting in your physics class when you get to college. You might see that the equation is expressed like this, where they put a G for gravity because they are dealing specifically only with the acceleration caused by gravity. In our class, I am not going to write a G on the board. I'm not going to give you two different versions of the equation because there are going to be times where I use this equation and A is -9.8. And then there's going to be other times where I use this equation and A is 0. And maybe other times where I use this equation and A is 2.15. The way that you know what value goes there is by understanding the story that goes with the question you're solving. So if this is a question about a car driving down the road, I'm not going to use -9.8. I mean, unless the car drove off a cliff and it is now falling, gravity is not causing the acceleration. It's the car, stepping on the gas or the brake in order to change the speed, right? So I'm going to leave it an A, and it's your job to know when to plug in that value for gravity. How are you supposed to know that? Well, for right now, if the object is falling, that acceleration is specifically the acceleration due to gravity. So when I work through problems with you, you might see me do this. And all I'm doing is I'm keeping the a as it is in the original equation, but I'm putting a subscript g just as a reminder that this acceleration for this story is caused by gravity, and so now I'm going to plug in a negative 9.8. For some of you, having that additional subscript will be really helpful as you do your practice work. For others of you, it won't be necessary. As an instructor, I'm not going to put G when we work through problems in this chapter or the next chapter. I am, however, going to put an A, and depending on the conversation, I might go ahead and throw a subscript of G up there just to get you more comfortable with understanding that we're using gravity or we're not using gravity, okay? All right, so this is the main idea that I need you to understand about free fall. So let's just recap real quickly. Let's go back up here to the top where we had all of the specifics laid out. Objects are falling, affected only by gravity. We're ignoring air resistance, and the rate at which the object accelerates is negative 9.8 meters per second squared, regardless of what our object is.